today. So I'm going to ask everyone to mute themselves, and also if you would turn off your video. We will start recording in a second, and it will help with the streaming and so on if you have your and the recording if you have your video off and your microphone muted. After I introduce Dr. Sargulzai, we will turn it over to him. I will turn off my video as well. Because we are recording it and timing, I think it's best to leave questions at the end. So he will go about 45 minutes, 40 to 45 minutes of presentation, and we'll have plenty of time to have questions and answers. And if there are lots of questions, we will have additional time. We can leave the Zoom on and the discussions can go on, but at some point we'll bring it to an end. And as I've noted in the previous seminars, we will be putting these on YouTube or some other media. We are just getting them edited at now. So let's see. I will start recording. Good afternoon. Welcome to our seminar series for new faculty in College of Engineering, Fall 2020. It's my pleasure to welcome you to the seminar given by Dr. Arman Sargulzai, who joined us in August of this year. And one of the things that certainly I think would impress many people, and certainly impressed me, was that I had to count the number of advanced degrees he has collected over the years. So it is rather unusual. I've only known one other person with so many degrees in the past. And he has electrical engineering master's and PhD obtained in 2012 and 2016 from Florida International University. He was, before coming to Tennessee Tech, he was also working there as a research assistant professor and institute director as well of Institute for Advanced Mobility. And he obtained a second master's degree in aerospace engineering in 2019 and second PhD in mechanical engineering from University of Florida in 2020. So if I counted right, that's 5 altogether, including his bachelor's degree. He has many years of experience in addition to his degrees, and his research is primarily on applying linear and nonlinear control methods, machine learning, and artificial intelligence to the field of network control systems. Obviously, these are areas that are quite applicable these days to autonomous driving, connected vehicles, and so on. And he particularly points out that he likes to use his skills and expertise to enhance the quality of life for people in areas of safety, security, and privacy concerns. He has already accumulated more than 60 articles, 2 active patents on his research efforts in security of control systems. He has presented in a number of international and national conferences and workshops, and chaired industrial and research workshops and training events. And he is already coming to Tech with an NSF grant, and he's continuing to build on his research area and collaborate with other faculty, as I've seen already. So with that introduction, I'm going to turn it over to Dr. Arman Sargulzai, Assistant Professor of Mechanical Engineering.
Thanks, Dr. Mutawalli. So hello, everyone. Thanks for attending my research presentation today. The topic of this presentation is security of networked control systems. I'm planning to discuss some of my research projects during this presentation. I hope it would be interesting for you to find out what kind of research I'm doing in my research laboratory. So first I will talk about my laboratory, Resilient Autonomous Network Control Systems, which I call it RANKS Lab. Then I will talk about network control systems in general. And then after that, I will talk about security of network control systems under false injection attack. And then after that, I will talk about methods in order to detect and compensate for another type of attack, which we call a time delayed switch attack, which we invented by ourselves on network control systems. And then finally, I will describe security of connected and autonomous vehicles. So before that, let me talk about myself a bit. I got my bachelor, master, and PhD in electrical engineering. I got my second master degree in aerospace and second PhD in mechanical engineering from University of Florida. This is my first semester at Tennessee Tech. It's my great pleasure to be here and my honor to be here at Tennessee Tech. And I'm looking forward to collaborate with other faculty members at Tennessee Tech. Before here, I was an assistant professor of electrical and computer engineering and director of Advanced Mobility Institute at Florida Polytechnic University. And before that, I was working in industry for several years where I was a lead engineer for 2 different products. My research focuses are security of network control systems, testing and verification of connected and autonomous vehicles, and also security of multi-agent control systems. So I would like to talk about RANKS, Resilient Autonomous Network Control System Laboratory, a bit. The RANKS lab's mission is to enhance the people's quality of life by assuring safety, security, privacy, and privacy concerns. We focus on multi-agent systems, robotic systems, autonomous and cyber physical systems. I would say 80% of our focus is on designing resilient and autonomous control algorithms. 10% is on attack prevention methods, which combine control and communication strategies. And 10% is on attack detection mechanisms using machine learning algorithms. Our research applications are connected and autonomous vehicles, unmanned aerial vehicles, mobile robots, robotic arms, and also smart grid systems. First, I will talk about network control system and its security to give you a brief introduction about what is network control systems and why security of network control systems are important. Network control system is a system that the loop is closed through the communication channels. So as you can see here, network control system can have one agent or multiple agents, such as centralized multi-agent control systems or decentralized multi-agent control systems. As you can see in the figure, the attacker or hacker, it can attack the system in multiple locations. For instance, I'm just trying to For instance, it can attack the supervisory control center. It can attack the communication channel between supervisory control system and controller. It can attack also the communication channel between sensory signal and communication channel and controller. So network control systems, they have a lot of applications. We can see applications in unmanned aerial vehicles, for instance, in search and rescue. We can see a lot of applications, robotics, such as manufacturing robotics, automated vehicles, mobile robots. We also see a lot of applications for network control systems in energy and power systems, such as smart grid systems. And finally, which is one of the most important ones, we can see a lot of applications for network control systems in transportation systems, such as connected and automated vehicles. Let me ask a question here. What is the difference? I want to know what is the difference between security 20 years ago and now? Obviously, if we think about it, we can say we only had data security issues in the past. Now security involves cyber physical systems and it can cost a life. So let's think about a scenario that I'm driving with a speed of 70 miles per hour. if a hacker hacked my system or my car or my vehicle in this case, while I'm turning in a curve and my vehicle doesn't turn or doesn't go through the curve, what is going to happen? So the difference between security 20 or 30 years ago and now is the fact that we are dealing with cyber physical systems and critical infrastructures. So that is my research. I'm looking at security of network control systems which have applications in critical infrastructures. A major cyber attacks, if I want to give you another example, a major cyber attack on US electrical grid can cause an economic loss of more than $1 trillion. That's a huge number. If we want to think about a cyber attack, although the 2003 Northeast blackout wasn't a cyber attack or wasn't caused because of a cyber attack, but let's, for a minute, for a second, let's imagine that it was. That specific incident affected 50 million people. That's a huge number. And also 11 deaths caused by that blackout. And more than $6 billion was the total cost for that incident. So that was fortunate that that specific event wasn't caused by cyber attack, but how if it was? How if attackers, they attack our smart grid? How if attackers, they attack our transportation systems or unmanned aerial vehicles? One of the main challenges with network control system is their security. Because of the connectivity on network control system, they are more exposed to different types of attacks. Addressing cybersecurity issues of network control system is a big challenge because we don't know what type of attack happened or occurred, when that attack has been injected to the system, and where has been injected. Also, attackers are becoming more intelligent. While we are coming up with new defense mechanism, also hackers and adversaries, they are trying to find more intelligent types of attacks. So what we should do, one of the things we need to do in order to come up with some defense mechanism is to model them. So how we can model attacks. Here we propose a generalized attack model. We consider an attack PI, which has access basically to several parts of a network control systems. So this attacker, it can attack delays and faults to measurement signals, reference signals, communication channels, and also control signals. So the functions and signals after attacks, we illustrate them with tilde. Obviously, I don't want to go through details of the model, but how can we model PI function? We modeled it as a linear function that injects delays and faults to the signals. This model covers most of the common attacks, such as false data injection attack and also time delay switch attack, which are really important and really important types of attacks. To illustrate the effect of FDI attacks on network control systems, we injected FDI attacks into our second follower in UAV's leader follower application. As you can see here, the left figure shows an acceptable tracking, while the second follower couldn't follow the leader due to the injection of FDI attack at a time of 60 seconds on the right figure, because we injected FDI attack at a time of 60 seconds. Here we injected FDI attack only into one agent in a consensus algorithm. Figure on the left illustrate consensus for 4 agents and 40 agents, and figure on the right, it shows those agents under consensus algorithm under FDI attacks. As you can see, the system cannot really go to a specific point that it was a desired point, and it's becoming unstable. So now, what are the solutions? So in order to talk about solutions, I came up with one simple example, which is a linear control system. So let's consider a network control system with a simple LTI system. Let's consider an optimal control case just for simplicity. So the system under attack with a probability of P is going to be under attack with probability of P. So we have a couple of solutions in order to solve or overcome this issue. The first solution is correct the received signal using estimation of attacks. The second type of solution is use the estimated signal for the control purposes. And then third solution, which simply we can say, let's drop this received signal and do nothing. But if we drop the signal, there are some other solutions which I'm going to talk about them as well. If we drop the signal, then we also have several other techniques to overcome the issue. We can reduce the probability of attack by redundancy in communication channels or improving the encryption algorithm. Some people, they might say this is costly, so there are some other types of solutions here. We can adapt the controller using secure control design techniques, or we can reconfigure the connectivity between agents or other parts of the system. So here I discuss one method to detect and mitigate FDI attacks in real time. Since FDI attack can make network control systems unstable or inefficient in some cases, it's necessary to detect FDI attacks in real time. I observed that most of the attention has been invested to detection of FDI attacks, while less attention was done on real-time mitigation and compensation. So usually researchers, based on the literature, use model-based learning algorithms to mitigate FDI attacks, but they require an accurate model of network control systems. Some researchers use learning-based techniques despite the fact that they require extensive computational efforts. So here we developed a secure control strategy to detect and mitigate FDI attacks using combination of model-based algorithm and learning-based algorithm in this specific research project. So we consider a network control system under unknown inputs, measurements, and process noises, and also FDI attacks. We consider some reasonable assumptions, such as Gaussian noises for measurement noise, and also bounded FDI attacks and bounded unknown inputs. First, we designed a state estimator based on our Lyapunov stability analysis, which uses neural network to estimate the FDI attacks in real time. The next thing we need to do, we designed, one of the things we needed to do, since measurements are noisy, we use extended Kalman filter to update neural network weights. Actually, this was really beneficial in our experimental analysis because we have measurement noises, and using this extended Kalman filter for updating neural network weights, it was really helpful and gave us more accurate results. And then finally, the controller is designed to be robust to unknown inputs. We defined the feedback signal based on our stability analysis, which uses the estimated FDI attack and output signals. We proved the stability of the system under FDI attack using this theorem, Theorem 1. I'm not going through this, the proof of this theorem, but I just want to talk about it briefly. We can show using this theorem that the state trajectories of the system under given assumptions with the state observer defined earlier and also the design controller are globally, uniformly, ultimately bounded, or we call it GUUB. You can find the proof and also more information about the proof in one of our submitted IEEE transactions paper. For the case study, we focused on centralized network control systems, and also we assumed two power systems that they are sending information to these centralized control systems. And this control system or these systems are under FDI attack, which FDI attacker or attacker can inject false to these communication channels. We investigated the accuracy of detected algorithm and performance of secure controller under 4 scenarios. First scenario is a single non-periodic FDI attacks, as you can see in the figures. The second scenario is single periodic FDI attack injected to one of the agents. And then in the next scenario, we check the performance of the developed controller for the system under multiple FDI attacks injected into both agents. And finally, we showed its accuracy under pulse train FDI attacks. It's clear through our numerical analysis that the performance of the detection and control algorithm are more accurate than the most recent methods in the literature. So now let me talk about another technique or another research topics that I'm focusing on. Here I will focus on TDS attack injected to network control systems with nonlinear dynamics. Here we developed a continuous controller for a network control system that is composed of agents with nonlinear dynamics. And those agents are subjected to TDS attacks and additive disturbances. The unique challenge that they had here was the fact that a state tracking error is unmeasurable because it's under attack. Therefore, controllers cannot use the state tracking error to coordinate the network control system formation. To address this issue, we came up with 2 novel error signals, which I'm going to talk about it in next slide. So here is the leader-follower network control system under TDS attack and disturbance. We consider that an attacker PI is injecting time delay to signals transmitted from agents to leaders. We assume that disturbances are bounded again, and also TDS attack is bounded. So the main objective of this research is to design a centralized controller such that the state tracks a virtual leader trajectory despite the injection of TDS attacks. The second objective for us is to design an observer to estimate the states of the network control system in real time. So here you can see all of our error signals, and these 2 are 2 novel error signals which we propose in order to overcome the issues with TDS attack. Based on the stability analysis, the control signal is designed, as you can see here, and U bar is the measurable feedback signal, and R is our novel error signal, which I mentioned in previous slide. Here is our observer design, which is used to calculate the auxiliary error signal. The observer uses neural network to estimate amount of delay injected to measurement signals, and the weight of neural network are updated based on these 2 equations, which are obtained through our stability analysis. We proved that the designed controller, a state estimator, and FDI attack compensator ensure a semi-globally, uniformly, ultimately bounded tracking provided the following sufficient conditions. So to show the proof, we defined a Lyapunov candidate function which includes error signals and also neural network estimation error. We also defined PLK, QLK, RLK, SLK, which are our LK functionals, which are necessarily when we deal with a stability analysis of systems with time delay. Taking the derivative of Lyapunov function in respect to time and using Cauchy-Schwarz inequality, we can obtain the following inequality. Using the mean value theorem and since TDS attacks are bounded, we can find this inequality, and then using this inequality and rearranging from previous inequality, we can find V dot as follows. We can further upper bound the previous inequality as shown here, and all these parameters, which are phi parameters, are positive values by satisfying those earlier sufficient conditions which I shared in the theorem. So with further simplification, we get this inequality, and using theorem 4.18 of Khalil's book, we can conclude semi-globally uniformly ultimately bounded tracking, which we were looking for it throughout this proof. For the simulation, we use a leader-follower formation control of unmanned aerial vehicles. The dynamic behavior of this system is given here with all those parameters. We injected a TDS attack to the follower based on TOW1, and also we injected additive disturbance based on D1, and we wanted the system or the follower and leader to follow the leader and visual trajectories, which is shown in this table. So our follower was able to track the leader under TDS attack and disturbances, as you can see in this figure. Here is the control signals of the follower under TDS attacks and also disturbances for both proposed control strategy and traditional strategy. To compare our results with the literature, we performed root mean square error analysis, and you can see the proposed controller is much better than the traditional controller under TDS attack. So another application of network control system is connected and autonomous vehicles. So let's discuss them briefly in order to find out how why security of those systems is important and how we should deal with that. Most of the current road accidents, almost 94% of them are results of human errors. We heard that autonomous vehicles, they are going to come by 2020, 2025, and still we don't have them, we don't have a complete solution because we have a lot of issues in this domain. And one of the main issues that we have is a trust on autonomous vehicles, safety and security of autonomous vehicles. I used to live in Gainesville when I was in Florida before joining Tennessee Tech, and I used to drive back and forth for almost 4 years. On average, I drove around 1,000 miles per week. So I would love to have an autonomous vehicle if you ask me, and if you offer me to have an autonomous vehicle, I would love to have it. And I can do a lot of different things. If I have an autonomous vehicle, I can do several different things, and I can be more I can do different, more different things if I'm driving really high or long distance. But if you ask me, can I trust those autonomous vehicles? My answer is a big no, because I do not trust a vehicle that can be attacked or an adversary can hack that system. So one of the main problems we have with autonomous vehicle is the fact that we don't have a framework or a specific systematic framework for testing and verification of those systems. And that is one of the research areas which Ranks Group is working on it. So there are several different challenges with autonomous vehicles. The first challenge is how many scenarios we have to generate and how we have to generate those scenarios in order to test and verify those vehicles. How to generate interesting edge cases. This is a really interesting and huge question. Do we need to test for all possible edge cases or all those scenarios? Can we eliminate similar scenarios using equivalent classes, and many other questions? Another main challenge which we have with autonomous vehicle is weather condition. How the perception of AV performs under electromagnetic interferences. how to test AVs and their perception under different weather conditions. And these are all different weather concerns which we have. And also, even though we are seeing autonomous vehicle on roads these days, we see also they have some crashes and they have some accidents. But there is no systematic way to learn those real world crashes and test vehicles under those crashes or under those already happened crashes. So that's another area of research we are focusing on. And finally, which is one of the challenges which I'm interested to work on it, is security of control of those autonomous and connected vehicles. How to test the stability of an autonomous vehicle in critical situations. How to test the stability of autonomous vehicles under faults, failures, and cyber physical attacks. In order to answer those questions, we started to come up with a framework which considers these challenges and generates scenarios in a modular way to test and verify connected and autonomous vehicles in hardware in the loop, vehicle in the loop, and real world environments. To give you one example, as a case study, I would like to briefly explain one of our research projects, which is related to security of cooperative adaptive cruise control. I'm sure all of you are familiar with cruise control. So we use it every day. I mean, if not every day, we use it a lot in highway. I mean, I used to use it every day when I was going back and forth to university and home. So cruise control is well known, but what is adaptive cruise control? Adaptive cruise control is using onboard sensors to adapt its desired speed based on the lead vehicle, using radar and LiDAR or some other sensors. While the cooperative adaptive cruise control uses the communication channel on top of onboard sensors to adapt its speed. So this is going to improve efficiency a lot if you use CACC or cooperative adaptive cruise control. Therefore, it can react faster to speed changes and it can follow the lead vehicle in more efficient manner. But how if there is an attack, or how if an attacker attacks the communication channel between vehicles and follower? So this research, we started to use, we designed a machine learning algorithm in order to detect false data injection attacks, which is injected to communication channels of these follower and leaders. And also we use a fuzzy-based control algorithm to adjust the speed and also adjust the distance between vehicles in the case that we have attacks in the system. So I just want to share, I don't want to go through the mathematics behind it, but I just want to share the results. We did test the proposed strategy in simulation under scenario, which is a really hard scenario. During the hard brake, we injected FDI attack or false data injection attack. As you can see in the figure 6, which is a left figure here, using the traditional method, a crash could be occurred, but using the proposed strategy, follower could follow the leader with without any accident. So here are some of my selected papers for more information related to my research, if you're interested to learn more. Also, there are some more papers here, more selected papers here for more information related to our research projects. So to conclude, I would like to share only 2 of our current projects, which we are doing at Tennessee Tech. And I think they are interesting, and we just started to work on those projects. So one of the projects is related to connected and autonomous vehicles. We are in the process of building an autonomous passenger vehicle. We plan to create a vehicle in the loop environment to test the vehicle autonomy under our simulated based scenario generator to test the system under critical scenarios, cyber attacks, and also different weather conditions. The scenarios and environments are simulated, but the vehicle is an actual vehicle. So that is going to make a perfect platform for us to test the vehicle under cyber attack situations. On top of the research, we are planning to use this platform for teaching, teaching courses, especially in our vehicle engineering and mechatronic concentrations. The second project which we are working on it, and some of my students right now they are working on it, is this modifying one of the already existed Formula SAE vehicles and make it autonomous. This allows us to engage students from mechanical engineering, electrical engineering, computer science, and other disciplines in the field of autonomous and connected vehicles. And also, hopefully, if we learn and use our experience with building this autonomous vehicle or autonomous race vehicle, we can hopefully attend some of those competitions, autonomous racing competitions in US and Europe in the future. So if you have any questions, you can ask. Also, if you want, you can send me an email after this presentation. You can also take a look at my website, which is ranks-lab.com, for more information about my research and our research directions. Thank you so much for your time, and I'm ready to answer any questions you may have.
Very well. Thank you so much for your presentation. You covered a lot of interesting and different topics. So we